This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We've got a nice frame analysis problem here. And just looking at the overall drawing of it, we have a two-member frame, continuous members ABC and DBE that meet at pin B. They're supported by pins also at points A and D down there on the bottom. The loads are as shown. Interestingly, I have a 6 kilonewton meter concentrated moment at C, and then a 12 kilonewton straight line force acting to the left at point E. I've got my dimensions, everything as shown. The first step in these problems is always to try to solve for reactions whatever I can, looking at the entire frame as a rigid body. So I'm just going to use the picture as my free body diagram and put those reactions at A and D, AY and DY up, I assume, and AX and DX I'm going to assume to the right. I want to try to guess, just assume something and drive on. Now I see that I can sum moments about, say, point D and eliminate dx, dy, and also ax as unknowns because it passes through D also. So before I even do that, though, I want to correct my units or get my units consistent. I've got 400 millimeters and I've got a 6 kilonewton meter moment. So I want to convert everything to meters. So 400 millimeters is 0.4 meters. 300 millimeters down in the horizontal direction is 0.3 meters. Now I've got consistent units. I can sum moments about point D on the entire frame. Counterclockwise is positive. That's equal to 0. So I've got negative for its direction of AY. It's trying to rotate clockwise, so it's negative AY times 0.3. And then I've got the 12 kilonewtons up top, trying to rotate counterclockwise, so it's positive 12 times 0.8, which is 0.4 plus 0.4 in the vertical direction. And then I have my concentrated moment, which is counterclockwise, so it's also positive 6. So my units are things like kilonewtons and meters, and this thing is in kilonewton meters. So it tries to rotate the whole frame, no matter where it's located, with a rotational force of 6 kilonewton meters, and that's what goes into my equation there. Now I do the math and rearrange. I get AY is equal to, this is 9.6, which is 12 times 0.8, plus 6, it's going to be 15.6, divided by 0.3 is going to equal to 52 kilonewtons, the direction that I assumed on my free body diagram. Then by the sum of the forces in the y direction, I could say by inspection, just by looking at it, that if AY is 52 kilonewtons up, there are no other y forces, therefore dy has to be the opposite and the same magnitude, 52 kilonewtons down. I want to use that on my broken apart free body diagrams. I can't solve for anything about AX and DX other than to know that they're equal, they add up to be 12 kilonewtons to the left. So I put my reactions on here as I know them. I kind of want to correct this one, dy, do it in green. dy is really 52 down, and AY is 52 up, like I assumed it. So therefore, I want to put those on these free body diagrams of the parts DBE and ABC. And so at A, I've got, this is really D, I'm sorry. This is point D, this is B, E, and this is A, ABC. Anyway, at point D, I have the opposite direction of that, 52 kilonewtons down. And I've got dx that I don't know what it is, I assume to the right. At the top at point E, I've got that 12 kilonewton force. And at B, the pin where the two members meet, I'm just going to assume by up and bx to the right on that member. On ABC, go to this other free body diagram. I've got AY, which I figured from the entire frame is 52 kilonewtons up. Don't know what AX is. Assume it like that. Then I've got this 6 kilonewton meter rotational concentrated moment up here. At B, on ABC, I need to assume the opposite direction, what I assumed on DBE. So I assume BY down on this one and to the left on this one for BX. Now look for an easy solution. If I look at member ABC and I sum moments like I usually do at the first time, I've got two unknowns still, BX and BY, because they don't align. But if I look at DBE, I can solve for BX by summing moments about point D. Let's do that in green. So I've got this is on DBE. And this can get quite complicated. This is an easy frame, but I need to make sure I'm looking at the right member. I got sum of moments about point D is equal to 0. Counterclockwise is positive. I've got at the top 12 kilonewtons, trying to rotate counterclockwise, so it's positive times 0.8, plus or minus, the only other thing creating moment that doesn't pass through point D is BX, and it's trying to rotate clockwise, so it's negative BX times 0.4. Do the math, this 12 times 0.8 is equal to 9.6. Therefore, BX is equal to, rearranging, 9.6 divided by 0.4, which is 24 positive kilonewtons. Positive means the direction I assumed, which is to the right on DBE. Now, I want to write that in. This is 24 kilonewtons. Same thing, opposite direction on ABC. And now on ABC, I can sum moments about point A. That's going to be equal to 0. And I've got up at the top positive 6 because it's counterclockwise, that concentrated moment. And I've got BX creating also positive moment, counterclockwise, 24 times 0.4. And I've got BY trying to rotate clockwise, so it's negative BY times 0.3. Okay, 24 times 0.4 is 9.6. There, rearranging, I have BY is equal to 6 plus 9.6 divided by 0.3. That's equal to 15.6 divided by 0.3 is 52 kilonewtons. The positive means it's the direction I assumed on ABC, so it's down on ABC. Therefore, it's up on DBE. It's 52 up on DBE and 52 down. Now I can check my work because I know these reactions. Just looking at ABC, I've got in the Y direction at the bottom 52 kilonewtons up, 52 kilonewtons down at BY, so that checks. If I wanted to solve for AX, it's going to be equal to the opposite to the right of this 24 kilonewtons from BX. So that's going to be equal to 24. And Checking on DBE, I've got 52 down at D, and I've got BY that I calculated as 52 up. So that checks. Those two add up to 0. Looking at the X forces, I have negative 12 at the top, 24 to the right. So this DX has got to be 12 to the left, which on the overall frame checks out because DX is really 12 to the left. AX is 24 to the right. 24 to the right minus the 12 at the top at point E, and the DX reaction also checks out to be 0.